Okay, we are going to start our last session for today, be followed by the reception. Lights are bright. Reminds me of that old song, "My future's so bright I need to wear shades." Well, I think our energy future is very bright, and we want to talk about that a little bit more this afternoon. We've already had some discussion about energy this morning in our legislative panel, and it's obviously very important to those folks at the panel as well as you at this crowd here. But so often that what's talked about in energy is the technology, be it solar panels or wind turbines or smart meters, battery storage, or the generation that we have. But what's not often talked about is how all of that is managed and the data and how important the data is to make it all work. So we've invited a speaker this afternoon to talk about that and where our future mix is going, how that will be managed. And so I'd like to introduce Dr. Chandu Visweswariah, President and Chief Executive Officer of Utopus Insights. This is a new venture in the energy analytics space that was launched in February 2017 with intellectual property from IBM Research and a strategic partnership with the Vermont Electric Company. Excuse me. Prior to co-founding Utopus, Chandu was the director of the Smarter Energy Research Institute at IBM's Thomas J. Watson Research Center. He was named an IBM Fellow in 2013, the highest technical honor confirmed by IBM. He led IBM Research worldwide efforts in smarter energy and environmental science. Excuse me. Prior to this position, Chandu was a distinguished engineer in electronic design automation in IBM's Systems and Technology Group, where he was responsible for correct signal timing in all IBM chips and drove the innovation and deployment of such innovation as statistical timing and automatic circuit tuning. He joined the IBM Research in 1989 after obtaining a PhD in computer engineering from Carnegie Mellon University. His numerous awards and over 100 publications and has 102 granted patents to his name. I could go on, but with that, it is my pleasure to welcome Dr. Chandu Visweswariah.
Good afternoon. Thank you very much, Mr. Bender, for that very kind introduction, and thank you to Governor Bevin and Mr. Bender for inviting me here this afternoon. Let me begin with just a few words about the Commonwealth of Kentucky. Mr. Bender assures me that this is one of the most friendly and hospitable states in the country. And so he encouraged me to make a few controversial comments and said that they would be well received. We have Fort Knox in Kentucky, and I've often mentally pictured Kentuckians counting their gold in their spare time in the afternoon, but I know that's far from the truth. We manufacture the country's most popular sedan here in Georgetown. We manufacture the most popular truck in Louisville, Kentucky. Right now, more than 90% of the world's bourbon whiskey comes from Kentucky, and there's something like 5.7 million barrels of bourbon that's aging as we speak in this Commonwealth. That's more than one barrel for every man, woman, and child in the state. That's quite impressive. We have quite a track record of breeding winners, and hopefully not just in horse racing. And we have inexpensive energy that's available to grow our manufacturing and economic ambitions in the Commonwealth of Kentucky. And I'm here to tell you that we need to rethink a little bit about this inexpensive energy that we have available in abundance for our manufacturing and economic base. Point number one, there are companies like Walmart or IKEA that require renewable energy to be part of their mix in order to open up new facilities in new states. IKEA has more than 92% of its stores powered by its own solar energy. And Microsoft has said that all of its new data centers will work on renewable energy. And so if we want to bring these employers into our state, at the very least, we need to allow them to install and permit and run this clean energy. But perhaps more importantly, we want to be supplying the cleanest and at least the least expensive form of energy to manufacturers and to employers. And the message I have for you is that that is no longer fossil fuel-based energy. And that's the message that I want to carry through my presentation as we look at why and what we need to do about that. There is a massive transformation going on in the energy space right before our eyes in broad daylight. The Union of Concerned Scientists did a ranking of states on progress in adopting to this massive energy transition and which states are leaning in to be well positioned in the future. And the winners in this ranking were California at number 1 and Vermont on the East Coast. Tiny Vermont was number 2 in their rankings. And this is where we have a collective groan, because Kentucky was rated 46th out of 50 states in leaning in and being ready for this transition. So what do we need to do? What is this transition? What does it mean? And this is what we will try to explain over the next 30 minutes. My presentation will be in 4 parts. We'll try to predict the future a little bit, as dangerous an activity as that is, and we'll look at it from the point of view of economic tipping points. Somebody said earlier today in one of the panels that it is all about economics. Leaving aside any subsidies of any kind, it's all about economics. We'll then take what we learn in terms of tipping points and try to understand how it's changing the energy systems and the grid, and the role that digitization will play in orchestrating these grids of the future. And finally, a call to action for Kentucky to participate in this coming energy transformation in a big way in order to be well positioned for the future. I'm going to begin with a couple of Wendell Berry teachings. I won't even call them quotations. Equally beloved by coal miners and tree huggers, equally beloved by blue states and red states. Hopefully we can say the same about my presentation when we finish, but he said, to save the future, live in the present. We should not let the present arrive in our absence. Pretty profound. Fairly predictably, we're going to be surprised by the future. I think Yogi Berra said predictions are tough, especially about the future. Same sentiment. All we can do to prepare rightly for tomorrow is to do the right thing today. If using less energy would be a good idea for the future, that is because it is a good idea, period. He said, what we must not do in our efforts of provision is to waste or permanently destroy anything of value. And he said, maybe we could give up saving the world and start living savingly in it. It's a new word of the English language, but it's a beautiful quotation. Changes in principle can be made now by so few as one of us. And that's something I try to live by in my own life. And finally, the future is coming at us faster than ever before. So the future is coming at us at 1 second per second, at 1 day per day. So that's a provably false statement. And I have a confession to make. That last quote there is from yours truly and not from Wendell Berry. So, is the future really coming at us faster? And if so, why? Let's take a minute to look at the internet. Courtesy of a company called Exponential, this is the amount of activity that happens on the internet in 1 minute. Look, for example, at the Amazon piece there. Amazon is selling $203,000 worth of goods in every minute on the internet, with no store in your neighborhood. Take Twitter, for example. There's 347,000 tweets every minute of every day on the internet. Some good, some not so good, but that's a lot of tweets. Now, let's take a quick show of hands. How many people in this audience use Google for searching? Most everybody. That's gone from 0 to 2.4 million searches per minute in the 19 years that Google has been in existence. I mean, that's astounding. How many people use email? Of course, almost everybody. And that's from 0 to 150 million per minute. And 25 years ago, unless you were in the Army or the Navy, you were not using email. How many people use Snapchat? Most people don't know what it is, but there aren't too many teenagers in this room. But believe it or not, it's gone from 0 to 1.8 million images per minute in the space of 6 years that the company has been in existence. So how many in this audience use Tinder? Stop. Do not answer that question. Do not answer that question. But believe it or not, Tinder has 972,000 swipes per minute, every minute of every day on the internet. I don't know what it says about our society, but it says a lot about the kind of technology that is fueling these amazing growth numbers. So I would argue that the staid and slow-moving energy industry needs to hitch a ride on the digital industry. Through a combination of cheap hardware, cloud software, and big data analytics, the digital industry is disrupting many other very staid industries. Without owning a single taxi, they are disrupting the taxi industry. Without owning a single hotel room, they are disrupting the hospitality industry. They change how we date, they change how we communicate, they change how we get our entertainment. And the time has come that the digital industry will disrupt the energy industry, which is a $6 trillion industry worldwide across electricity, transportation, building, heating, and cooling, is ripe for a massive change. Now, these massive changes are captured here as exponential and disruptive megatrends. Megatrend number 1 is the availability of data. So, in our grids, we have SCADA that's providing us voltage and current data. We have PMUs on our transmission side. Every wind turbine has measurements and sensors. We have weather data, we have vegetation data, we have soil data, we have forestry data. We have data coming out of our ears. And by one estimate, we will have 150 petabytes of grid data per year by the year 2020. And if most people don't know what a petabyte is, it's 1 followed by 15 zeros. This is an unbelievable amount of data that's going to be available to us. The second is the renewable explosion. Solar and wind are on cost curves. The statement I'm about to make is not about subsidies, it's not about politics, it's all about economics. Solar panels are getting cheaper year over year. We're getting more and more clever at harnessing energy from every sub-band in the frequency of visible light to get more energy out of it. And there's another 2x in efficiency that's on its way to commercialization from the laboratory. Wind is also on a cost curve. At some point, they achieve grid parity, where the levelized cost of energy delivered is equal to or better than a conventional source of energy. And when that happens, there's a giant sucking sound, and future investments go into the cheapest form of energy. And that's why, once you achieve that tipping point, you get exponential growth in the renewable energy. It is, however, an intermittent source of energy, and we'll talk about that some more as we go along. The third big D is the distributed nature of the grid that we're going to see. So the first D was digitization, the second D is decarbonization, and the third one is the decentralization of our energy sources. So our grid was kind of built to have big centralized production of energy, transmission, distribution, and then consumption behind the meter. Well, that's being thrown into complete turmoil with solar panels here, wind farms there, production of energy everywhere, batteries everywhere, and so on. A very, very distributed grid. And finally, coming towards the end of the decade would be the explosion in battery storage and electric vehicles. There are so many battery chemistries that are being tried, and today they are expensive, but they are also on a cost curve. And when they reach some sort of magic number around $130 or $150 per kilowatt hour, there will be an exponential increase. These tipping points are very, very important because they give us an indication of what is going to ramp up very rapidly in the future. And there's not a day when you don't see evidence of these tipping points in the newspapers. Volvo says it will stop making conventional gas vehicles. The UK says that in 2040 they will not allow you to sell gasoline vehicles. There's more and more evidence that these are very real tipping points that are coming at us. So let's talk a little bit about these tipping points. This picture that you see is a study that was conducted by UT Austin in December of 2016. They went county by county through the entire United States and asked the following question. If I were to build a new power plant, what fuel source would I use to get the least expensive cost of energy delivered to the grid? And as you can see, there's a big swath in the middle of the United States and much of the Northeast where the answer is wind. There are big areas where methane or natural gas wins that battle. And then there's pockets of nuclear. And in the Southwest, as you'd imagine, there's big pockets of solar. And coal is nowhere. In other words, if I were to build a new plant today, I would not build a coal plant almost anywhere in the country. But this was in 2016, we're in 2017. Things have changed already. Prices have moved. Wind has gotten cheaper. Offshore wind is coming. In fact, the entire eastern seaboard of the United States has this geological gift of a shallow outer continental shelf, which means that you can get leases there for your wind turbines, and Long Island will be the first to be entirely powered by offshore wind. And there's already 13 leases that have been negotiated. And what about the West Coast? There are floating wind turbines that are coming. These are at the 4 to 6 megawatt level. They're gigantic. And the beauty of floating wind turbines is that 2/3 of the Earth's surface suddenly becomes useful space to have your wind turbines. You don't have to pin them to the floor of the ocean, and you can mass produce them. So with both solar and wind, there's more advances coming that will drive down the cost of energy. And if today 2/3 of the country has wind and solar as the cheapest form of energy, those areas are just going to grow over time as we go forward. Here's a tipping point for you. In the year 2015, worldwide, there was $234 billion spent on conventional energy generation investments. And for the first time in history, there was more spent on renewable sources at $268 billion. That's a real tipping point. And here's another one for you. Oil and gas investment worldwide in 2016 was $708 billion. And for the first time in human history, there was more spending in the electricity sector than the oil and gas sector at $718 billion. That's representing the trend towards more electrification that we are seeing all over the world. And yet another one for you. Nuclear generation in March of 2016, for the first time in 33 years, was outpaced by renewable generation across the United States. And of course, coal is next. So in fact, wind and solar will do to methane and natural gas what methane and natural gas are doing to coal right now. In that sense, methane and natural gas are a transition fuel towards the future. So, electrification is something that I mentioned, and we're seeing that as a big trend going forward, but it's a networked trend, and I'll explain that in a moment. Electric vehicles are coming, and why are they attractive? They're attractive because they're 3 times more efficient than gasoline-powered vehicles. Having explosions in steel chambers to get locomotion produces noise and heat and dust and all of these things that we don't want, and it's so much more efficient with an electric motor. Likewise, heat pumps are about 4 times more efficient than a conventional furnace. Industrial processes can be electrified, and you can get gains anywhere from 50% to 10x. LED bulbs are 6 times more efficient than traditional incandescent bulbs. Water heaters are more efficient than gas heaters. And I couldn't resist putting this on here because the cover of IEEE Spectrum had a whole study on electric planes and how we're going to electrify air transport. But I'll grant you that that's a little bit more into the future. The whole point of this electrification is it does a couple of interesting things. It gives us efficiency, which on the one hand saves us money, and that's a good thing. But it also gives us flexibility. Because if I have a water heater, I can decide to heat my water a few minutes later or a few minutes earlier, and as long as I have a tank of hot water, nobody's going to notice the difference. The same with heating and cooling, conditioning of spaces. The same with your electric vehicle. I can charge your car at 9 o'clock at night or midnight or 2 in the morning because the wind is blowing nicely. You wouldn't know the difference as long as it's charged up by the morning. So this beneficial electrification is also giving us the flexibility that we need to use the cheapest form of energy, which happens to be intermittent and requires that flexibility. It is a beautiful synergy, and I'll explain as we go forward. So, just to wrap up the first section on tipping points are caused by economics. They're not caused by tree hugging, they're not caused by blue states. They're caused truly by economics. Because subsidies get you only so far, it needs to be an economic win for it to really take over the world. Tipping points are inexorable. You cannot bring back the buggy whip industry. It's just inexorable. And tipping points are then followed by mass adoption. And we're lucky and fortunate that we live in a time when, over the next 6 years, we're going to see 4 tipping points right in front of our eyes, interconnected with each other and enabling each other to propel us forward. So let's take a look at how our energy systems and grid are changing as a result of these tipping points. I will now introduce you to something called a Sankey diagram. Many of you may or may not have seen what a Sankey diagram is. Let me take a moment to explain. A Sankey diagram is just a flow diagram. For example, if I have money coming in from a salary and an allowance, that's money flowing in, and then I spend money on various things that's going out. So you'll see a series of pipes with energy coming in and energy going out, and the thickness of each pipe represents the amount of energy that's coming in and out. So bear with me while I explain this, and I hope it will be beneficial for us. I'm going to use the state of Vermont as an example, and I'm going to show you the Sankey diagram for the entire energy use of the state of Vermont in the year 2015, and then a projection to the year 2050 so that you can compare and contrast. So in 2015, the energy mix is as shown on the left. It's mostly fossil. This energy mix is across transportation, buildings, and electricity. And there's a little bit of hydro, a little bit of nuclear, and a little bit of bio. These pipes show the movement of electricity from a primary fuel into the blue electricity box, which means it changes from nuclear, for example, to electricity. And you see how much of that is flowing. You see that the electricity now feeds buildings and industry, and to a very small extent, transportation. The 2 EVs in the state of Vermont, perhaps. You also see now that each of these 3 components, buildings, industry, and transportation, has useful energy and wasted energy. And as we all know, our use of energy is extremely wasteful. Just to give you an example, if I have an incandescent bulb, I want light. But if it produces heat, that's a waste of energy. One example of wasted energy. When you look to the right-hand side of this diagram, the productive amount of energy is much smaller than the wasted energy. We are in an industry that is not even 50% efficient. Imagine if we operated an airline where only 50% of the seats were used, or we ran a hotel chain where less than 50% of the rooms were used at any time. That would be a disaster. But that is the state of our energy industry today. We waste more energy than we use productively. And you see, a lot of that waste is coming from transportation, and a reasonable amount is coming from buildings. And industry is somewhat efficient, not producing as much waste as those other sectors. So now, if you superpose the tipping points from section 1 onto this diagram, first of all, if internal combustion engines give way to electric vehicles, then instead of getting the energy from fossil fuel, transportation would get that energy from the electricity blue box and would become more efficient in the process. Similarly, if furnaces gave way to heat pumps, you would again see buildings getting more of their energy for heating and cooling from the electricity box, and that piece would become 3 to 4 times more efficient. Similarly, if fossil turbines are going to give way to solar and wind, you'll see the electricity blue box getting its primary fuel from the hydro-solar wind column. So let's take a look and try to visualize what this will look like as we go forward. I'll start from the right-hand side. The first observation, and what I'm going to show you along the bottom, working from right to left, will be the situation in 2050. It's a projection. Point number 1, the productive energy far outpaces the wasted energy. In other words, this $6 trillion worldwide industry we're talking about has an opportunity to get so much more efficient. Then you see where the wastes are coming from. It's still a fair bit from transportation and almost nothing from buildings and industry. So we've made buildings a lot more efficient. Then you see the electricity box that's feeding industry and transportation and buildings a lot more than it was before. And finally, you see the primary energy mix evolving very, very rapidly in the scheme of things to being hydro, solar, wind, and bio, given Vermont, which is not that dissimilar to Kentucky. There'd be a lot of wood chips and biogas and and so on, and a small sliver of fossil, to get rid of which you would have to go after every boat and every lawnmower and every plane and so on, right? So this is exactly the comprehensive energy plan that Vermont has put together to achieve greater than 90% decarbonization by the year 2050. Now, what are the implications of this new energy mix? Let's think about today's grid and compare it to tomorrow's grid. First of all, today's grid is very centralized with one-way flow of power from primary generation down to the meters. And instead, we're going to have a distributed grid with production of energy everywhere, including rooftops. And so you'll have omnidirectional or bidirectional flow of power. Secondly, the amount of uncertainty will increase. So today we have a little bit of uncertainty in that we predict tomorrow's demand for electricity and we plan to have enough energy, and you can't predict that perfectly. But the amount of uncertainty is going to reach a whole new level because we will be so weather dependent. You'll be dependent on the clouds, you'll be dependent on the wind. Thirdly, the role of a consumer is going to change. We think of them today as ratepayers. They pay a bill once a month based on a volumetric use of electricity. And instead, they will be so-called prosumers. They will both produce and consume electricity, and perhaps get a little bit more involved in the policies of when their car gets charged and when their heat pump is running and how much they're willing to pay for all of these services, and whether they can provide some flexibility back to the grid. Volumetric sales will clearly give way to new business models. We had a good discussion earlier today about net metering and whether our bills should get unbundled, disaggregated, and that will clearly happen. Things like demand charges will just become a thing of the past. Time of use billing will become prevalent. It's clear. Today, generation follows load. For the most part, we don't do too much of demand side management. We predict the load and make sure we have enough energy. That's going to fundamentally change, where we try to use the flexibility in the load to match generation. And finally, the way you run the grid will change from a much more daily or static planning to real-time optimization and digitization while understanding all of the uncertainties. To illustrate this, I want to just give you a simple English explanation of what all of this digitization means. It just means that we'll be heavily dependent on wind and solar for our energy needs, and that's not a problem. So we have one situation when energy is scarce because the wind's not blowing, it's nighttime. You have another situation where wind is abundant, solar is abundant, and in fact, electricity is free because the fuel is free, so you just have more energy than you know what to do with. And then you have every situation in between. So if you have something like a dishwasher that you could run in the evening or you could run at night, it's a very flexible load that can be run either just now because energy is available, or run it later when you get a signal that energy is available. Batteries will discharge when supply is scarce and then charge when it's plentiful. An electric vehicle is just a battery on wheels, and it would behave the same way. All of our diverse power sources, whether it's nuclear, natural gas, wind, solar, society would just rank order them in terms of expensiveness, taking into account carbonization if that's important to society. And you would simply curtail expensive power when energy is abundant, or turn it on when necessary to keep the reliability of the grid. The same thing with heating and cooling of buildings. If I preheat or pre-cool by 2 degrees, you wouldn't know the difference, but I can literally swing megawatts of load by doing this. So in some sense, we keep saying the grid is going towards DER, or distributed energy resources, and the nickname I use for it is really a digital energy revolution, because you will use information to make all of these different decisions to keep the grid balanced in real time. And so to wrap up this section on the grid, the power sector is going through a massive transformation. We're going to use cheaper forms of energy, i.e. solar and wind. They are intermittent. It needs a new type of intelligence to forecast and optimize and run the grid. It will be cheaper. It will have less waste. It will be cleaner. It will be better. It will be more reliable. But in order for us to achieve this transformation, there are three legs of this stool. We need all of the technology. We need batteries to get cheaper. We need PV to get cheaper. We need wind to progress. We need offshore to get better. We need digitization, which is all the intelligence to forecast and orchestrate the grid. And then we need policy and business models to unbundle our electric bills, to get rid of those demand charges, to allow real-time pricing so that the market will help us to balance the grid in an autonomic fashion. On to the third main part of my presentation here, which is the role of digitization. I'd like to just take two brief examples of where digitization has really made a difference in the way we run our electric grids. Not to say that these are great examples, they are, but to give you a glimpse of what is coming in the future. The first example I'll give you is some work that we have done with Velco. Velco is a Vermont electric power company. They are the transmission authority across the state of Vermont, and they are owned in turn by 17 distribution utilities. They have invested in smart meters. They have invested in a fiber network across the entire state, which is extremely helpful. I don't expect you to read all of the boxes here, but at a high level, we ingest all of the data that's available. And we have over 100 gigabytes of data gushing through this system on a daily basis, and it keeps getting more as time goes on. So principle number one, we use all the data sources we can get. We then curate that data automatically in a common or canonical format so that we can build models and do our optimization on it. Number three, we invest in specialized high-resolution proprietary weather forecasting so that we can literally track every cloud that passes through and every gust of wind. We know the wind at pole level to know whether poles are going to fall in a storm. We know the wind at hub height level, so we know how much wind energy we'll get from our turbines. We use all of that weather data to build machine learning models that allow us to predict wind power production, solar power production, as well as demand for electricity, taking into account behind-the-meter photovoltaics. So if there are solar panels behind the meter, that's taken into account in these predictions. We finally put all these forecasts together, along with the uncertainty thereof, into a model of the grid that allows us to predict energy imbalance, power quality issues, congestion problems, and so on, so that we can build a plan to orchestrate that grid and keep itself balanced over the next 15-minute increments, the next 6-hour increments, and so on. And out of this comes an ability to integrate ever higher amounts of intermittent solar and wind energy while dealing with problems like balancing, power quality, congestion, and so on. This is the intelligence that's helping us to orchestrate this grid. Here's a little animation that shows what our proprietary weather forecasting looks like. This is across the state of Vermont. The color on the floor shows the precipitation, and you see a little bit of rain near Rutland. You see sometimes the wind is very laminar in flow and sometimes gets very turbulent. And you see the wind speed shown by the color of the arrows, and the arrows show the wind direction. So this is called hyperlocal weather forecasting. It's fundamentally different from what the National Weather Service would do, which is at a 12-kilometer resolution. This is at a 1-kilometer or sub-1-kilometer resolution, which is what permits us to predict wind and solar energy with something like 95% accuracy. Now, when you can predict energy availability with 95% accuracy, it doesn't stop it from being intermittent, but it makes it perfectly dispatchable. That's the difference with the good forecasting. One more quick example of digitization. Many of you are aware of these Nest thermostats, and Nest was bought by Google. And in 2 or 3 different parts of the country, Nest runs a program called the Rush Hour Rewards Program. And here's how it works. Nest works with the local utility to provide you, the consumer, with a thermostat. And it may be free or it may be discounted. You then enter into an agreement with your utility that if there is a peak situation, the utility can turn down your heat by up to 2 degrees. You won't feel the difference. 10 minutes later, the peak passes, and then it'll heat up your house again. Nobody knows better, but they can swing 20, 30, 40 megawatts of load minute by minute, and then bring the load right back. Here's an example of a win-win where, using the internet, centrally, somebody is swinging a lot of load. The consumer is benefiting because they're getting a thermostat, they're saving money. The utility is benefiting because they're dealing with their peaks. They don't have to build additional transmission. They don't have to invest more iron in the ground. It's a perfect win-win-win with digitization. These two are just examples of the kind of digitization that we will need going into the future. So at the end of the day, renewables are going to grow because they are the cheapest form of energy, not any other reason. Secondly, that is an intermittent source, and so we need forecasting and intelligence to integrate all that renewable energy. That in turn enables us to electrify transportation, heating, and cooling, which A, makes it more efficient, and B, gives us the flexibility that with our digitization we will control in order to integrate all of that in. And therefore, the summary here of the transforming grid is that the future grid will have a lot of sensors all over it. There'll be smart meters, SCADA, PMUs, weather data, weather stations. All of this data will pour into some central intelligence. That central intelligence will have weather forecasting, demand forecasting, stochastic optimization, machine learning built in, and we'll come up with actuation that says, here's some pricing signals, here's when we should charge the car, here's when we should open these relays, here's where we have power quality problems. And in some sort of energy cloud, which is transactive in nature, all of this will be self-balanced in an autonomic fashion. That's where I see the grid going. So let me end with a call to action for Kentucky and for this audience here. A few takeaway messages, if I may repeat them. Ignore exponential trends at your peril. They are inexorable. Winning technologies are determined not by subsidies, not by political leanings. They are determined by economics, ultimately. And embrace digital data and the insights thereof, because they will become inherently what we need to run and orchestrate our grids going forward. And so I would ask the question, does Kentucky have a long-term energy plan on the energy mix? I would ask the question whether we are beginning to look at our tariffs and our business models and ask ourselves, are we setting up the right incentives to be on top of this transformation? Are we business friendly? If a Walmart wants to come here, if an IKEA wants to come here, can they get a bidirectional connection and permit within 24 hours? That's what you have to do to compete with Iowa to win business these days. And finally, are we in fact business friendly and cloud friendly? Remember, a lot of this is going to be enabled by the cloud. And I would even ask, are our utilities in the state of Kentucky allowed to purchase cloud solutions for their software? Or are we using old-fashioned notions of capitalizing our purchases and saying no to cloud technology, which is what is going to be inherent here. And so I would just ask you to take a moment and try to imagine what would happen if Kentucky's unbridled spirit really embraced this energy transformation. We've had a great ride with coal, we have cheap energy, we have a lot of manufacturing, but things are changing, and are we prepared for this rapidly changing future? So I'll conclude once again with some words from Wendell Berry. The right thing to do today, as always, is to stop or start stopping our habit of wasting and poisoning the good and beautiful things of the world, which once were called divine gifts and now are called natural resources. Only the present good is good. It's the presence of good work, good thoughts, good acts, good places, by which we know that the present does not have to be a nightmare of the future. The kingdom of heaven is at hand, because if not at hand, it is nowhere. Thank you very much.